In this spreadsheet video, we're going to be building a very simple source sink population model. And you might remember that Jed indicated that a source is a subpopulation where the birth rates exceed the death rates, and when there's a carrying capacity in the source population, the source has to send individuals out of the source population, and it exports those individuals to the sink population. And in contrast, the sink is a subpopulation where the birth rate is lower than the death rate, and that population would go extinct if it were isolated. However, it can persist by receiving immigrants that came from the source population. So we'll be modeling these dynamics in this particular video. If you've downloaded the spreadsheet template, you'll see this setup here. We've set up a timeline from 0 to 200 down column A. So our time step is going to be 1 unit, that is a year. So there's one time step is equal to 1 year. We'll be modeling the source population in columns B through G. We'll be modeling the sink subpopulation in columns H through M, and we'll be looking at the total system in columns N through S. So that would be the source and the sink together. For our inputs, we have these BIDE rates that Jed mentioned. Let's look at the source population first. Let's assume that the source population has a per capita birth rate of 0.7 and a per capita death rate of 0.6. Now, if this population were isolated, it would grow, right? Because the birth rate exceeds the death rate. And it would grow, but in this case, we're going to cap its growth according to this carrying capacity. And we'll assume that there are 100 places or territories that can be occupied in the source habitat. So the population will grow until it reaches 100. At that point, the source will begin to export individuals to the sink. We'll let the immigration to the source be 0. That means that this source population is going to grow strictly from births and not by receiving immigrants from someplace else. And this emigration is going to be actually defined by the model itself. So it's shaded blue as an output. That means that it emerges from the model as an output rather than being an input directly. We'll see how that works in just a second. So let's go ahead and start modeling the source population. We'll do that in columns B through G. Our starting population size will be entered in cell B10, and we'll start with 50 individuals. The per capita birth rate, 0.7, combined with the number of individuals will give us the total births. So in cell C10, we're going to calculate the total number of offspring that were born in that very first time step. Remember what that is? You got it. It's just going to be the number of individuals times the per capita birth rate. And we'll need to anchor our reference to cell B3. The result is 35 individuals. And in entering that equation, we've made a few really important assumptions about our model. Can you think what they are? Two big ones come to mind. The first is that every single individual here is able to breed. And that means that we are modeling an all-female model. So these are all females, and they're able to reproduce, and they reproduce at this particular rate. The second thing that comes to mind right off the bat is that there's no age structure. We start off with 50 females, and each and every one of those individuals is able to give birth. So there's no age structure in this model, and once again, it's an all-female model. How about the deaths? Well, the deaths is going to be the number of individuals present in the population times the per capita death rate. Once again, let's anchor that, and that gives us the number of deaths in this particular time step. Immigrants, we said the immigration rate was 0, but let's go ahead and count the immigrants. It's going to be the number of individuals in that time step times the per capita immigration rate. So these rates are per individual rates, per capita rates. So in order to calculate them, we just multiply the number times the rate, and that gives us the number of births, deaths, immigrants. Now, how about the emigrants? Well, remember, we said that the source will happily grow until it reaches this carrying capacity. And so as long as our number of individuals plus the new births, subtract off the deaths, plus the immigrants, as long as that is all less than the carrying capacity, then we will have 0 emigrants. There's no need for any individuals to leave. However, if this number of individuals plus births minus deaths plus immigrants exceeds the carrying capacity, we'll need to force some of those individuals out. Now, how would you enter that in as an equation? Give it a try. Put your video on pause and then give that the best shot you can, and we'll come back. There's probably a few different ways we can handle this. How'd you do? In my mind, there's a few ways we can do this. Probably one of the easiest ways is to use a simple if function. Let's find that if function. And remember that an if function has 3 arguments. The first is the logical test. The second argument is what do you want the spreadsheet to return if the logical test is true. And the third argument is what do you want the spreadsheet to return if the logical test is false. So our logical test is going to be whether or not the number of individuals plus the births minus the deaths plus the immigrants is less than the carrying capacity. So we'll enter that in. B10 plus the births, C10, minus the deaths, D10, plus the immigrants, and we're asking, is that less than or equal to the carrying capacity? And you can see that Excel is returning the word true. So if it is true, then we need to say that the number of emigrants is going to be 0. There's no need for anybody to leave the source because we're below the carrying capacity. What if we are above the carrying capacity? Well, then we need to calculate how many individuals we are above the carrying capacity. So that would be B10 plus C10 minus D10 plus E10, and then we're going to subtract off K and anchor that reference to K, so it's minus 45. Now, in this case, we don't have to worry about that because our population is well below carrying capacity, and so we will return, or the spreadsheet will return, a 0 for 0 immigrants. However, if we do exceed the carrying capacity, then this result would calculate how many individuals in excess of this carrying capacity we are. Make sense? Our emigration rate now is going to be calculated down column G, and this is going to be the number of emigrants per person, per female, and that's simply going to be the ratio of those two. And we'll be able to drag these equations down in just a second. Now, what about the sink population? Let's assume that the sink population is also 50 individuals. And when I say sink population, what I really am referring to is a subpopulation, because technically these are one giant population and they are somewhat isolated from each other. The source and the sink each have their own unique birth and death rates. So there's some spatial structuring happening here. They're not freely mixing. However, they do interact through this process of dispersal, and so technically people would refer to these as subpopulations. We'll compute the birth, death, and emigration rate the same way we have for the source population. So we need some inputs here. Remember that the sink subpopulation has a birth rate that is lower than the death rate. And in the absence of immigration, it would go extinct. We're going to say that the individuals in the sink don't emigrate from the sink. They're there, they're sort of stuck there. But we are going to let the sink receive immigrants from the source. And here's our connection right here. These immigrants are going to end up in the sink population. So let's calculate the births in the sink. Right? That's going to be the number of individuals in the sink times the per capita birth rate. Anchor that. The number of deaths is going to be the number of individuals in the sink times the per capita death rate for the sink. Anchor the reference to cell C4. And the number of immigrants is simply going to be what? It's going to be the number of immigrants that are coming from the source population. So we've just made the connection between the source and the sink through this process. And now the number of emigrants is simply going to be the number of individuals times the emigration rate, which we said was 0, and we'll anchor that reference. And we'll calculate our immigration rate now as the number of immigrants per individual that are currently in the population. So it's cell K10 divided by cell H10. Make sense? So it's really a very simple extension of a basic population model. Now the last step is for us to consider all of these individuals together. And as you can guess, this is going to be pretty easy. The total system at time step 0, we begin with 50 individuals in the source plus 50 individuals in the sink. So that's B10 plus H10. Our total births are the total births from the source and all the births from the sink. Our total deaths are going to be the deaths from the source and the deaths from the sink. Our immigrants are going to be the number of immigrants that changed subpopulations. So how many new individuals entered the source plus how many new individuals entered the sink. Same thing goes for the immigrants. How many individuals left the source and how many individuals left the sink. And at this point we're going to be able to calculate lambda, and we'll do that in our next step. We're going to be now projecting the population through time. So we need an equation here in cell B11 for the source and in cell H11 for the sink, and that would be the equation that really puts our population dynamics together into one generating equation. Put your video on pause again and see if you can take a shot at entering those two equations, and at that point our model is pretty much done. We just have to calculate lambda. So I'll see you in just a minute.